As we move towards more sophisticated applications of reinforcement learning, the complexity of the problems we tackle increases dramatically. This complexity often manifests as high-dimensional state and action spaces, making it challenging for agents to learn effective policies. Imagine a self-driving car navigating a busy city street. It needs to process information from numerous sensors, tracking the positions and speeds of other vehicles, pedestrians, traffic signals, and more. This deluge of data creates a high-dimensional state space, making it difficult for the agent to comprehend and act upon. This phenomenon, often referred to as the curse of dimensionality, poses a significant challenge for traditional reinforcement learning algorithms. As the number of dimensions increases, the amount of data required to learn an effective policy grows exponentially, making learning intractable. This underscores the need for new algorithms and techniques that can efficiently handle high-dimensional data and extract meaningful patterns from complex environments. Researchers are actively exploring various approaches to mitigate the curse of dimensionality. These include techniques for dimensionality reduction, such as feature extraction and representation learning, which aim to compress the state space into a more manageable form without losing crucial information. Additionally, hierarchical reinforcement learning methods break down complex tasks into smaller, more manageable subtasks, allowing agents to learn more effectively in high-dimensional environments. A persistent challenge in reinforcement learning is achieving stable and reliable learning. Unlike supervised learning, where models are trained on static data sets, reinforcement learning agents learn by interacting with dynamic environments. This dynamic interaction can introduce instability in the learning process, making it difficult for agents to converge to optimal policies or, in some cases, even causing them to diverge altogether. One source of instability stems from the delayed nature of rewards in many real-world applications. An agent might take a sequence of actions where only the final action leads to a significant reward, making it challenging to attribute credit to the preceding actions that contributed to the eventual success. This credit assignment problem is a fundamental challenge in reinforcement learning, requiring algorithms that can effectively propagate rewards back in time to appropriately update the values of earlier actions. Another source of instability arises from the exploration-exploitation dilemma. An agent that explores too aggressively risks destabilizing its learning by constantly trying new actions without reinforcing the ones that have proven successful. Conversely, an agent that focuses too heavily on exploitation might converge to a suboptimal policy, missing out on potentially better solutions. Finding the right balance between exploration and exploitation is crucial for stable and efficient learning. Section 4. Towards generalization. Bridging the gap from simulation to reality. A significant challenge in deploying reinforcement learning agents in the real world lies in ensuring that the skills they learn in simulated environments transfer seamlessly to real-world scenarios. Simulations provide a safe and controlled setting for agents to learn, allowing them to make mistakes and try different approaches without real-world consequences. However, the real world is messy, unpredictable, and rarely conforms perfectly to the neat models we create in simulations. This discrepancy between simulation and reality, often referred to as the sim-to-real gap, poses a significant challenge for deploying reinforcement learning agents in real-world applications. An agent that performs flawlessly in a simulated environment might fail miserably when faced with the complexities and nuances of the real world. This highlights the need for robust training procedures and algorithms that can bridge this gap, enabling agents to generalize their learned skills to new, unseen situations. Researchers are actively exploring various approaches to address the sim-to-real gap. These include techniques for domain adaptation, which aim to minimize the discrepancy between the source, simulation, and target, real-world domains, and transfer learning, which leverages knowledge gained from one task or environment to improve performance on a related but different task or environment. Additionally, techniques for building more realistic and robust simulations, incorporating elements of uncertainty and noise, are crucial for bridging the sim-to-real divide and enabling the deployment of reliable reinforcement learning agents in the real world. Learning from interaction, a paradigm shift in AI. As we've journeyed through the world of reinforcement learning, from its fundamental principles to its transformative applications, One overarching theme emerges: the power of learning from interaction. This paradigm shift in artificial intelligence, moving away from passive learning from static datasets towards active learning through trial and error, is unlocking unprecedented capabilities in machines. No longer are we confined to programming explicit instructions for every scenario. Instead, we can now create agents that learn and adapt, discovering novel solutions to complex problems through their own experiences. This paradigm shift is akin to the transition from rote memorization to experiential learning in humans. Just as a child learns to ride a bike not by studying equations, but by experimenting, falling, and adjusting their balance, reinforcement learning agents acquire skills through direct interaction with their environments. This approach, deeply rooted in the principles of trial and error, feedback, and adaptation, is proving to be remarkably effective in imbuing machines with a level of intelligence and problem-solving prowess once thought to be the exclusive domain of humans. This shift towards learning from interaction represents a fundamental change in how we think about and design intelligent systems. It opens up exciting possibilities for creating machines that can operate autonomously in complex, dynamic environments, learning from their mistakes, and continuously improving their performance over time. As we continue to explore the frontiers of reinforcement learning, we are witnessing a profound transformation in the landscape of artificial intelligence, one that promises to reshape our world in ways we are only beginning to imagine. The road ahead, charting the future of reinforcement learning. The journey of reinforcement learning is far from over. In fact, it feels like we're only just beginning to scratch the surface of its true potential. The road ahead is filled with exciting challenges and opportunities, beckoning researchers, practitioners, and enthusiasts alike to push the boundaries of what's possible in the realm of intelligent systems. As we venture further into this uncharted territory, several key themes emerge, guiding our exploration and shaping the future of reinforcement learning. One prominent theme is the pursuit of more efficient and scalable learning algorithms. Current reinforcement learning methods, while powerful, can be computationally expensive and data-intensive, often requiring vast amounts of training data and processing power. Developing more efficient algorithms that can learn from fewer examples, generalize better to new situations, and operate effectively in real-time environments is crucial for unlocking the full potential of reinforcement learning across a wider range of applications. Another crucial aspect is the development of more robust and reliable reinforcement learning systems. As these systems become increasingly integrated into our lives, from self-driving cars to personalized healthcare, ensuring their safety, fairness, and trustworthiness becomes paramount. This requires developing new methods for verifying the behavior of reinforcement learning agents, ensuring their actions align with human values and objectives, and creating mechanisms for human oversight and intervention when necessary. Embracing the unknown, a call to exploration and discovery. The field of reinforcement learning is a testament to the power of exploration and discovery. Just as early explorers embarked on perilous journeys into uncharted territories, researchers in reinforcement learning are constantly pushing the boundaries of knowledge, venturing into new theoretical landscapes, and developing innovative algorithms to tackle increasingly complex challenges. This spirit of exploration, driven by a thirst for knowledge and a desire to create truly intelligent machines, lies at the heart of this rapidly evolving field. As we continue to explore the frontiers of reinforcement learning, it's crucial to embrace the unknown, to be open to new ideas and approaches, and to challenge conventional thinking. The answers to the most pressing questions in reinforcement learning won't be found solely in textbooks or research papers. They will emerge from the collective creativity, collaboration, and relentless experimentation of a vibrant community of researchers, practitioners, and enthusiasts united by a shared passion for advancing the field. The journey ahead is filled with challenges, setbacks, and moments of doubt, but it is also paved with the thrill of discovery, the satisfaction of overcoming obstacles, and the immense potential to create technologies that will reshape our world for the better. As we embark on this exciting journey, let us embrace the unknown with open minds, a spirit of collaboration, and an unwavering commitment to pushing the boundaries of what's possible in the realm of intelligent systems.